Chapter 4, Section 5, Determination of Protein and Biomolecular Structures. There's a whole section of science that crosses biology, crosses chemistry. There's an area of science we refer to as structural biology. Structural biology literally is what it sounds like. You're studying the structure of certain biomolecules, certain proteins, nucleic acids, whatever. You're going through trying to discern the shape so you can see how shape actually determines the true function. Because yeah, I can go through in a cell biology lab and I can study the function of an enzyme. In biochemistry lab, we can study the activity. You know, what's the K max, what's the V max, all that stuff. But a structural biologist, a structural biochemist, is going to go and look at the overall three-dimensional structure. Those are the people that usually give us the ribbon models and things like that. And discern the different motifs and the different domains that are actually necessary for that function to occur. The information you're going to be able to get, well, it's going to come from different procedures, different type of assays, different types of, laboratory methods. One of the big ones is what is referred to as X-ray crystallography. You take your macromolecule of interest or your molecule of interest, if you're a pure chemist, you crystallize it. You crystallize it by turning it into a salt. So you take it, you make it a salt crystal, whether it's a protein, nucleic acid, or some other form of organic compound, organic molecule, or whatever. Different methods for different things. And you take that crystal and you bombard it. Bombard it with an X-ray beam, okay? Not a broad like you would if you were getting an X-ray at the hospital. It's a very narrow beam X-ray. And the pattern you'll get off of that crystal, because each of the different amino acids is going to form a different part of that overall crystal shape. It's going to hit, and you're going to expose that beam and those refracted X-ray beams. You're going to expose them to X-ray film, or nowadays they do it. They have different sensors. I guess for lack of a better term, sensors that will detect where X-rays are bombarding it. And as you can see here, they'll go through, they'll look at that pattern, and they'll use some higher level math, high level calculus, to do what's referred to as a Fourier Transformation. So they take that pattern and they start to fill it in. Go through, fill it in, as you see there in B, and discern based on this, pattern, what amino acids have to be there and where to get this overall pattern. Remember, different amino acids, different shapes. Some of them aren't going to work too well close together, things like that. And you start filling it in. And then you go through and put all that data into a computer, and voila, it gives you D. Here's a ribbon model, which we've seen before: alpha helices, beta strands, and anything that may be held within. What you're looking at here is myoglobin. The red in that thing that's in the center of the ring here, that's the heme. But we have to keep in mind that forming the crystal is not natural. It is going to change the conformation somewhat, or some of them it's going to change it quite a bit. So making the crystal will disrupt what should be the native conformation in an aqueous solution. So they've now put in some of the math in some of the more contemporary programs that do this, that will do the calculations. That's one thing early on. Well, here's the structure, and they kept getting different structures for the same thing, different labs. And it turns out it was the slight variances in their crystallization method led to slight differences in the crystal, which led to. So now they take it and they're trying to get it to a point where the crystal-derived structures that you see with X-ray crystallography will give us what we think of as the functional conformation. We'll see. NMR is another mechanism you can use for getting the structure of a protein. Nuclear magnetic resonance, NMR. Turns out all the atoms in your body have a specific spin pattern. Even the atoms that are caught up in the amino acids that make up your polypeptides and the polypeptides that make up all your proteins. They have specific spins, and the spin pattern is still going to be there no matter what structure you're talking about. Any changes in conformation, still going to have a spin pattern. It just may be offset now. Instead of being like this, around like this, change in the conformation, it's still like this. So those are the things that we can go through and we can look at. Nuclear NMR, as I said, looks at the nuclear spin patterns of certain atoms: hydrogen, carbon, nitrogen, fluorine, and phosphorus. Okay, we're not going to go through and measure all the different ones that could be there. These are the majority of them. Okay, not going to worry about sulfur, not going to worry about oxygen, whatnot. This spin, remember that spin, sets up a very minute dipole. Well, you go through and you measure the dipole. You go through, put everything under a magnetic field and distort that dipole. Remove the field, see how everything bounces back. Compare the two. And then you go through and you look at, what they call the shift. Is that the exact, if you were to go through and talk to somebody who does NMR, is that the exact way they would explain it? Oh, God, no. As I have said in lecture many times, live lectures and these tape lectures, I'm an end user. I show up to the lab that does the NMR, that core facility, and I hand them my stuff and say, please measure this. They give me a file of data, the data which I can then go and plug into programs that will give me the shapes and this and that. Now, there's more modern day ways of looking at it, what they call two-dimensional. Two-dimensional, either nosy or toxy. They're going to have slight variations to what we were talking about there. These slight variations in timing, what you're measuring, how you're measuring it, they think gives us a better overall idea of the structure. You look here to the just above my head, you'll notice that this structure has some ghostings. Well, turns out with these 2D methods, it gives us, here's the best guess and most probable guesses, which is why you see here the dark ribbon and then some lighter ghosted ribbons. Well, here's what the shape could be, based on confirmation and based on the data. But that's still, you're making a crystal, or you're doing something like that. What happens instead of crystallizing, you just froze it. That's what this cryo-electron microscopy is. Instead of going through and making some, crystal of or things like that, you freeze it in place. take some non-crystalline ice, because the ice crystals will interfere with everything. So you want some vitreous, very cold, holds everything in place. The ice is such that it's not going to have large crystals, cracks and things, bubbles and whatnot. So it's very purified water and things that are added to it to give it this specific quality. You don't have to take into account the changes in the conformation due to crystallization, like you do with what we've talked about previously. It's better for, depending, structures, large dynamic things where you have way too many carbons, way too many hydrogens and things like that to sit there and be able to, based on the numbers, try to figure out the overall structure. And you look at the crystalline. You look at the crystals, as you see here, top left there. Crystals of a chaperonin protein known as GRO-L. Based on the structures, based on the way it looks, they're able to, back in, get going the back door to come in with. Here would have to be the overall secondary, tertiary structures to give us this type of a shape. We know what amino acids are there because there's many, you can do a sequencing and things like that. Here's, carbons, nitrogen, here's the alanines, isoleucines, stuff like that. And you can go through and the computer can sit there and calculate, well, here's what would have to be there to give this overall shape. They've also done it with, human telomerase, as you see here above my head.